Eli did his PhD in University of Arizona in 2013, and followed that up with a postdoctoral work at the University of Oregon for 2 years. Then he moved to the University of Lausanne, and he's been there since then and has done a lot of different measurements in different systems, including garnets, zircons. I think he worked on quartz as well. And today he'll be talking about the diffusion and anisotropy of titanium in zircon and implications for titanium in zircon thermometry. So Eli, it's all yours.
Well, thank you, Sumit. So let me get this. Can everyone see this all right?
Yeah.
Okay. So yeah, thank you all for coming and sticking around for this talk. So I'm going to be talking today about some experiments we've been doing for about the past 2 years, which has really been aimed at trying to quantify the diffusion anisotropy of titanium and zircon and explore what the implications of these data are for titanium and zircon thermometry. So before I jump straight into what we've done in this study, given we've got a very large group here, I want to just spend a minute talking about why we care so much about zircon and why this has become such a highly studied mineral. So in my opinion, I would say that there are two major points that make zircon such a useful mineral. The first of which is that there are a lot of very well calibrated geochemical techniques that we can apply to this mineral. So for example, we can get very good uranium lead ages out of zircon. We can relatively easily measure both stable and radiogenic isotopes within zircon and retrieve all kinds of useful information from these data. What I'll be talking about for most of today is we can measure titanium concentrations in zircon and from this retrieve temperatures. And much more recently, zircon has emerged as a potentially very powerful diffusion chronometer. So the second reason I would say zircon has become such an important mineral is that it's just very common. So the upper continental crust is a very complex unit. It's very heterogeneous. And as it turns out, we find zircon in a very large cross range of the different rock types within the upper continental crust. So in addition to having all of these great techniques that we can use on zircon, we just find this everywhere. So it's a very great mineral to be able to sort of apply the same techniques across a very wide range of lithologies. Given this is going to be a focal point of this topic, I want to just quickly go over the very basics of how titanium and zircon thermometry works. So this is a figure that I've borrowed from Ferry and Watson from 2007. This is really the end result of a study in which they essentially grew zircon from a number of different starting materials and showed very nicely that the concentration of titanium within zircon is a very strong function of temperature. So what makes this so useful is that we can take zircon from any given rock, measure the titanium concentrations, and as long as we have some sort of reasonable constraints on what other phases were around when zircon was crystallizing, we can get a temperature from this. Now, to give an idea why this is so worth spending the time on, as of about 4 days ago, I looked this up, and this thermometer has been cited almost 1,500 times since 2007. So this is an extremely commonly used thermometer. And I would say there's two main reasons for this. Number one, as I just said a moment ago, given zircon is such a ubiquitous mineral, it just makes this thermometer very easy and very useful to apply to a large range of rocks. And the second reason is because it's been shown that titanium diffuses very, very slowly within zircon. So what I'm showing here are, in this lower curve, these are diffusion coefficients for titanium and zircon reported by Cherniak and Watson in 2007. And for sake of comparison, I've also plotted on here iron magnesium diffusion coefficients from olivine, which I've borrowed from Domen et al. 2007. And the reason I specifically borrowed iron, magnesium, and olivine is this is what I would consider to be sort of a middle of the road diffuser in terms of the rate of diffusion. As we just heard in our previous talk, this is very commonly used to look at sort of magmatic timescales. And you can see right away that these diffusion coefficients for titanium and zircon are much, much lower than this. So I will show a few more quantitative examples in just a few slides, but the end result from this chart, the really take-home message is that these titanium diffuses so slowly in zircon, according to this data set, that under essentially any crustal conditions we're going to encounter on Earth, we can basically assume that diffusion will not be a major factor in modifying titanium concentrations once zircon's crystallized. Now, this makes this thermometer all the more appealing for two reasons. First, it makes it easy to apply. I mean, we don't have to sort of think about how to model how diffusion may have modified the concentrations we're looking at. And it means that we're always getting a crystallization temperature from zircon, which by and large, I would say is usually what we're interested in when we're applying different thermobarometric systems. So that is what I've talked about so far has basically been sort of introduction to what we're working on. So moving forward, I want to go through the problem that we're working on, and this has to do with the diffusion anisotropy we expect to see in tetragonal minerals such as zircon. I want to move on to talking about the experiments we've done, for which I'll go through the way we've designed these experiments. I want to very quickly go over analytical techniques that we used in this study. And the reason I want to go over that quickly is because I want to spend more time talking about what the implications of this data set are for titanium and zircon thermometry. And if I have time, I might go over a bit of what the implications of these data are for other diffusing species in zircon, particularly other tetravalent cations in zircon. Okay, so when we're dealing with an anisotropic mineral, we're dealing with something in which physical properties within this mineral have the capacity to be dependent upon orientation. Now, it's always very nice when we're dealing with an isotropic mineral, just because this takes a very considerable layer of complexity off the table right up front. But the good news is that if we're going to deal with an anisotropic system, tetragonal mineral is going to be the next easiest thing to deal with. So in terms of kind of conceptualizing the diffusion anisotropy we expect to see, I think the easiest way to visualize this is to look at this in terms of the tetragonal unit cell. So we can think of this as starting with a uniform cube and just stretching this along the c-axis. Now, what this means in terms of the crystallographic axes within a tetragonal mineral is that the A and B crystallographic axes will be identical to one another, and the c-axis will be something different. So in terms of physical properties, including diffusion coefficient, this means that if we're looking at anything within the AB plane, then as long as all of our other variables are constant, diffusion coefficient will be constant as well. Now, as soon as we leave that AB plane, we have the possibility that that diffusion coefficient could change. And if there is significant anisotropy, we expect that looking orthogonally to that plane or parallel to the c-axis is where we should see the maximum degree of diffusion anisotropy. Now, just because we're dealing with an anisotropic mineral, this doesn't guarantee that diffusion coefficient or any other physical properties are going to be significantly anisotropic. But nonetheless, we do have to take a look at this and see if we can measure any sort of difference. Now, going back to titanium diffusion in zircon, it turns out that the study done previously by Cherniak and Watson only looked at diffusion occurring perpendicular to the c-axis, so only looking at diffusion within this AB plane. And again, I mean, just because we're dealing with an anisotropic mineral, this doesn't guarantee we will see significant anisotropy. But starting this study, sort of our line of thinking was, well, if all we do is verify that titanium diffusion in zircon is very slow parallel to the c-axis, that's very useful information to know for sure and not have to assume. And if we find something different, then that could be very interesting. So all of the experiments we did were performed on gem quality zircon crystals. The bulk of these zircons came from the Central Highlands of Vietnam, although a good 6 or 8 experiments were done on zircon megacrystal that came from Tanzania. So given the main variable we're interested in this study is anisotropy, the first step was to determine the orientation of these crystals. So the way we do this is using single crystal X-ray diffractometry. And this is pretty straightforward. We essentially just take a diffraction pattern from every visible crystal face we see. Once we have enough of these, we can determine the orientation of the entire crystal. And ultimately, we end up cutting these beautiful crystals into a bunch of roughly 3 millimeter cubes. And the final step here is that we take a cut surface that is perpendicular to the direction in which we want to measure diffusion and polish this really just to as high a degree of polish as we can. And the idea here is that ultimately we want a very large, very uniform, very flat diffusion interface for titanium to diffuse into. So in terms of the charges that we actually heated up, this is a pretty simple experimental design. So we took our cut-oriented zircons and then packed them within platinum crucibles into a source powder, which is composed of various stable phase assemblages and also designed so that this will introduce an influx of titanium throughout the diffusion anneals. Now, the source powders themselves, I'm going to go over this pretty quickly, and it'll be very obvious in just a slide or two why I'm going over it quickly. But we did use quite a few different source powders in this study. And what we wanted to do was design powders so that we were systematically introducing different major element activities and titanium concentrations in these experiments. So some systems, it's been shown that major element activities such as silica activity can impose a pretty strong control on diffusion coefficients. In other systems, it doesn't seem to matter. Likewise, concentrations of the diffusants themselves can influence your diffusion coefficient. In other systems, it doesn't matter. But since we're going through the trouble of doing a whole nother round of experiments here, we thought we might as well make a bunch of source powders and look for all this stuff. The experiments themselves were predominantly done in box furnaces in which we just heated up these zircons in air. Although we did run, I think, a good 7 or 8 experiments at a much lower oxygen fugacity just to make sure that wasn't a significant variable affecting diffusion coefficient as well. Okay, so just really I'm not really doing this justice going through this quickly. This was a large part of this study, but I just wanted to touch on the 3 main analytical techniques we use to measure these profiles. So I'd say a good 30% of these experiments we analyzed using laser ablation ICP-MS. Now, this is a great technique when you've got relatively long profiles over about 20, 25 microns. Laser ablation ICP-MS has very good sensitivity. You can collect data very quickly. The only real drawback to this technique is that given we have a fairly wide beam, I think the smallest width of a beam we had in this study was about 6 microns. You really need, at least 15, ideally more like 20, 25 microns to really get a profile that's not completely convolved. But if you have that, it's a fantastic technique. The next major technique we used was SIMS depth profiling. And this is kind of on the opposite end of the spectrum. So this is a fantastic technique when you've got very short profiles. So just to look at the difference between what we measure with these 2 techniques. For laser ablation ICP-MS, we're measuring profiles up to a few hundred microns in length. When we do SIMS depth profiling, we're looking more at the scale of a few hundred nanometers. So we can measure very short profiles with one technique, very long profiles with another. I would say SIMS depth profiling is very good up to about 2 microns. It certainly works for profiles longer than that. It just becomes very, very long to collect these profiles. So for a handful of these experiments, we analyzed them using nanoSIM step scanning. And this just sort of provided a very nice middle ground to these 2 techniques, between about 3 and 20 microns. It's a very good technique. So combining all 3 of these techniques, ultimately what this gives us is the ability to conduct experiments at a very large range of temperatures where we're going to expect very different lengths of titanium diffusion profiles. Okay, so this essentially is the end result of about 2 years worth of experiments here. So I'm just plotting the diffusion coefficients of titanium we've measured against reciprocal temperature. These different symbols and the different colors of the symbols all correspond to these different source powders that I talked about a few slides ago. And the reason I said I wanted to go over that pretty quickly was because we ultimately couldn't detect any resolvable difference in diffusion coefficient across experiments that impose different major element activities or different titanium concentrations. Now, on the one hand, this was a lot of extra work to get, a sort of lackluster result, but at the end of the day, I think this is good news. both because this makes it easier to apply our data to natural samples and that we don't have to constrain, what these variables look like when diffusion was occurring. And because in terms of fitting the data, we can just apply a global fit to all of these diffusion coefficients. Now, if I add to this chart the data that was collected by Cherniak and Watson, in which diffusion occurred perpendicular to the c-axis, you can see right away that there is a very large degree of diffusion anisotropy here. Now, I want to mention at this point that we did perform a handful of experiments in this study in which we looked at diffusion perpendicular to the c-axis, but we stopped this pretty quickly because it became obvious that we were really just getting maximum diffusivities that were completely consistent with this previous study. So what I'm showing here are the results of an experiment in which we ran 2 zircons at once that were prepped differently, so that in one we had diffusion occurring parallel to the c-axis, another in which diffusion was occurring perpendicular to the c-axis. And as you can see, parallel to the c-axis, we induce about a 200 micron profile, whereas perpendicular to the c-axis, this is too short to even really reliably pull out a diffusion coefficient. Now, this was an experiment run at 1450 degrees for almost 2 months. So it's pretty hot for a pretty long time, and we still get very, very little diffusion perpendicular to the c-axis. So we decided it probably wasn't worth doing a ton of these experiments, since, again, we were really just recreating this data set reported about 15 years ago. So in terms of the extent of anisotropy, if we take the lowest temperature that's shared by these 2 experimental studies, which is 1350 degrees, there is about 4.5 orders of magnitude difference between the diffusion coefficients parallel and perpendicular to the c-axis. Now, you can probably see that these are diverging as you go down in temperature. And in fact, if we extrapolate this down to about 950 to 600 degrees, which I would say is, roughly going to be the temperature range that's really more relevant for igneous zircon crystallization, that difference increases to about 7.5 to 11 orders of magnitude. So this is a very significant degree of diffusion anisotropy that we've observed here. It turns out there's a very good explanation for why we see this extent of anisotropy. So what I'm showing here are just 2 images of the zircon crystal structure. On the left is an image in which we're looking down the crystallographic c-axis, and on the right, we're looking perpendicular to that axis. So on the left, you can see that there are quite a few fairly large interstitial sites within the zircon crystal structure, and these are all perfectly channelized down the c-axis. So on the one hand, it's very difficult in these sorts of studies to really nail down where our trace diffusants are sitting in the crystal lattice. But it seems very, very likely that that titanium is able to exploit these channels for very rapid diffusion down the c-axis, whereas it simply doesn't have this option if it's diffusing perpendicular to the c-axis. So in terms of now turning to what the implications of this new data set is for titanium and zircon thermometry, I think this has some important implications that I'll get into. But just as important as that, I want to start really by saying what this does not mean. And the reason I want to start with this is because as I was starting to collect these diffusion coefficients and seeing really what a big difference there is, whether you're looking at diffusion parallel or perpendicular to the c-axis, my first reaction was definitely to think, okay, well, can we ever really trust these temperatures we're getting with titanium and zircon thermometry? If diffusion is this much faster, do we just reset our titanium concentrations all the time? And I'm going to try and convince you now that no, that is not the case. So it's important to bear in mind that even though we see this very large difference, these diffusion coefficients reported for titanium perpendicular to the c-axis are some of the slowest diffusion coefficients that have been measured in geologic material. So even though we have much faster diffusion parallel to the c-axis, this is still not a very fast diffusing species. What I would say this does mean is I don't think it's a wise idea from this point forward to just sort of inherently assume that titanium and zircon won't be reset under any crustal conditions. And I think that for any given rock we're looking at, we really need to sort of think about what temperatures did this see, what are the potential temperature time paths this went through, how fast did it cool, Could reheating have happened? All this sort of has to go into making a well-informed interpretation of whether our titanium concentrations are giving us a crystallization temperature or whether this has been modified by diffusion somehow. So to sort of drive that point home, I've got a handful of pretty simple calculations to go through here. So this is very, very simple. So all I've done here is take a zircon where I impose an initially homogeneous condition of, I think I imposed three parts per million zircon, then gave it a boundary condition of 100 parts per million, and then modeled isothermal diffusion, both perpendicular to C and parallel to see sort of how long it's going to take to get any sort of significant diffusion occurring. So taking the data for titanium diffusion perpendicular to the C-axis, if we hold this zircon at 1,000 degrees for 100 million years, we expect just under 2 microns of diffusion distance. If we hold it there for 1 billion years, we expect about 5 microns. And if we hold it at 1,000 degrees for the entire age of the Earth, we get a little less than 10 microns diffusion distance. So this is, I guess, a more quantitative way of saying what I said earlier, that this data basically says we don't need to worry about diffusion of titanium and zircon under crustal conditions, at least perpendicular to the C-axis. Now, if I do these same calculations, taking this new data set in which diffusion occurs parallel to the C-axis, it's a much, much different story. So at 1,000 degrees parallel to C, in as little as 1,000 years, we expect over 10 microns diffusion distance. In 15,000 years, we've already got 50 microns of diffusion penetration going here. Now, we can keep playing this game, just extrapolating these data sets down temperature at 850 degrees parallel to C. I would say we're still in a realm where we can have significant modification of our titanium concentrations at geological timescales, but it's a different ballgame. Instead of 1 to 15,000 years, we're looking at 1 to 15 million years. So it's a different sort of geological process that's going to lead to disruption of the titanium and zircon thermometer if we're dealing with lower temperatures like 850. Now, if we take this down to 750 degrees, we're really right back where we started at 1,000 degrees with diffusion perpendicular to C, in that we need hundreds of millions to billions of years to really do anything significant. And really, we probably don't need to worry about this. Now, this is a very significant thing to point out because a lot of titanium and zircon temperatures come from the range of about 600 to 800 degrees. So there's a bit going on in this chart. Let me just unpack what I'm showing here. So this is essentially the same as the last chart, in which I'm showing data we collected in this study and data reported by Cherniak and Watts in 2007. I've just zoomed this way out to where we can see what it really looks like when we start extrapolating this down to the lower temperatures where we actually, really care about what's happening geologically. Now, as you can, sorry, I should explain this gray band, getting ahead of myself. So this gray band we're seeing here is really just the scaled probability density of about 17,000 titanium and zircon measurements that we took from the GeoRock database to give some idea sort of what the global distribution of titanium and zircon temperatures is. And the takeaway here is the majority of them, as I said, come from about 600 to 800 degrees, which is in this lower temperature range where we probably don't need to worry about this in a lot of scenarios. Now, there is a caveat to this, and that is basically has to do with the fact that even though these data say we should have very slow diffusion at these lower temperatures, we are extrapolating these data very, very far. Now, when we do this, there are two sort of problems that come into effect here. First, our error envelopes are going to increase quite a bit. Now, that's a very dealable problem. We can just apply our minimum and maximum diffusivities whenever we're doing geological modeling. But in addition to that, we also have to assume that this trend maintains linearity throughout a very large temperature range. And that may be the case, and in some cases, it may not be the case. So this is a figure that I've borrowed from Chakraborty 1997, which is basically showing how these sort of kinks can develop in Arrhenius trends based on these different diffusion domains. Now, to be fair, this is a very qualitative diagram. And even if there is a kink in this Arrhenius trend, it could be a very mild kink that has very little impact, or it could be a major kink that really starts to change things. In addition to that, where such a kink pops up would matter quite a bit. So if our activation energy becomes lighter at a very low temperature, around 600 degrees. This really won't have any geological implications. I mean, things are diffusing so slowly at that temperature, it doesn't really matter if we change the slope at that point. At the same time, if this happens up around 900 degrees, then extrapolations of this data set could be a bit misleading in terms of just how fast things are diffusing at those temperatures. To be 100% clear, I am definitely deep in the realm of speculation at this point. Over the range of data we have, we don't see these kinks, but I do think it's very important to be aware of these sorts of things when you're making an extrapolation of, down temperature 400 degrees, these sorts of things can happen. Okay, so just to wrap up, I think I had 3 major points here. The main finding of this study is that titanium diffusion in zircon is quite anisotropic, and that diffusion parallel to the C-axis happens much faster than diffusion perpendicular to the C-axis. We don't find any dependence of titanium and zircon upon major element activity, titanium concentration, or oxygen fugacity. And in terms of what this means for titanium and zircon thermometry, my impression at this point is this puts us in a situation where in many cases, we probably still are getting crystallization temperatures from titanium and zircon measurements. However, I think we need to be a bit more judicious moving forward in how we interpret these things. So lastly, I just want to say that this was really a team effort, this entire study. We collected data in a lot of different labs, and I had a lot of great collaborators, so I just want to thank them. I won't go through this list, but this is everyone involved in this study, and I think that's it. So thank you.
Thank you, Elias. So that was a very nice description, I thought, of how an experimental study works, how you go about actually measuring diffusion coefficients. So aside from titanium and zircon, this was a very good introduction, I thought, for people who do not actually work in an experimental lab all the time. So thank you for that. And with that, we set things up for questions again. And the same game, you can type something into the chat, or you can ask questions, unmute yourself. So I am assuming Gerhard's hand is up from the last talk. You just didn't take it down, or?
Yes, I will take it.
All right, okay. And Ralph has a question.
Yeah, thank you, Eli, for this very nice talk and your good data. So I was wondering, so you use different sources for the titanium in your experiments, imposing different activity of silica and titanium dioxide to also get different concentrations. So are your concentrations at the rim, are they consistent with the titanium and zircon thermometer?
Yeah, the experiment, I wish I had made a figure of this. The experiments in which we had a titanium phase are consistent. Of course, when we get into the ones that are, 100 ppm, 10 ppm, that changes quite a bit. But, experiments where we had, say, rutile or Sri Lankite there, it's consistent with what we expect from the thermometer, yes.
Okay, good. Yeah, I was just asking because I don't really remember the details of the paper of Cherniak, but usually they have to impose very high concentration because they measure the profiles using Weatherford backscattering, which is nice because it allows you to measure very short profiles, which is important for this very slow diffusion coefficients. But also, yeah, I'm not sure if are their concentrations consistent with the thermometer, or do they have higher concentrations? I don't remember.
I would have to go back and look at that. I'm hopefully remembering this correctly to do their work justice, but I believe in those, the sources were ground up zircon and rutile. At least most of their experiments. They did a few things we didn't do. They did some experiments that had fluid phases present and things like that, which we would like to do, and I think will do. It's just a matter of, do we want to wait another year and a half to publish this stuff? Yeah, I don't know if the concentrations themselves were reported, but based on their sources, I would imagine that it's probably pretty realistic what they did.
Yeah. Okay. Thank you.
Okay. So we have a number of questions have come in on the chat. So Igor Vila is asking, what could be the diffusivity of a larger ion such as hafnium? What would you expect it to be?
Yeah, let me see. I think I have something for this. Sorry, all my anticipated questions here. Yeah, so that is something we've thought about quite a bit, because it turns out that the studies looking at uranium, thorium, and hafnium diffusion in zircon also all only looked at diffusion occurring perpendicular to the c-axis. So now on the one hand, I think that what we've found warrants going and doing some more experiments. I don't know that we would see this same degree of anisotropy in any of these other species, largely just looking at the size of these different ions. So these, we're attributing this fast diffusion parallel to the c-axis to these interstitial sites that are really highly channelized. The size of these sites is very well suited to titanium. Now, when you get into zirconium, hafnium, this isn't that much bigger. So it wouldn't surprise me if some hafnium, some zirconium, maybe in isotopic, disequilibrium could exploit these channels. We really just need the experiments to know for sure. Getting into something like uranium and thorium, again, we need the experiments to really know. But I mean, my guess would be that we probably don't see that same degree of anisotropy with something this much bigger. It just would surprise me if you could squeeze those big ions through these channels. But I mean, that's the long answer to say, I don't know. So I hope that answers your question, Igor.
It may,
Yeah,
but
thanks.
Doesn't let you off, because the next question, which was there before all of this came up from Gerhard, says, what about the potential effect on anisotropy of something like lithium? That's small.
Yeah. So I'm sorry, just to make sure I'm understanding the question, you're asking if lithium could show the same degree of anisotropy, or whether lithium would have an effect on other diffusants?
No, if lithium would show anisotropy.
Yeah, that's a great question, because that's a fairly large ion, but it's monovalent. I think it does. Yeah, I don't have this to show. I mean, we've done a few preliminary experiments looking at lithium diffusion parallel to the c-axis, and we've seen really, really fast diffusion. But to be fair, I don't have enough experiments there to really say a whole lot about it. I need to sort of replicate those initial experiments and then move forward and start to get something more systematic before I say too much. But yeah, no, I mean, I think these are all valid questions. And I mean, unfortunately, the answer to a lot of it is that I think we need to do quite a few more experiments on zircon to clear these things up.
On lithium, you have two different issues going on. First of all, it's much faster. So if there's an anisotropy, the effect might become more geologically relevant than some of the things. And the other thing is that there's already been shown that it diffuses by two different mechanisms.
Yes.
It could become quite a interesting twist and turn in there.
Yeah. And I'll go a step further and say, I believe lithium probably has more than just two it could diffuse by, but I think that's probably a pretty complicated system in zircon.
Okay. So look at lithium is the message. Then I have two questions from Matty, and I don't know if you want to unmute and ask it yourself, or should I be reading it out? I could do either way. So just wait, because I don't see anybody here. Let's start reading it out. So the first question is how the diffusion occurs perpendicular to the c-axis, as the atomic size of titanium is quite larger than the size of the channels in that direction. So you were talking about it just now. And one thing is understood, that the major channels in zircon crystals are along the c-axis. That is why it is faster along parallel to the c-axis, right? There are few studies, Sadune et al. 2008, Bengston et al. 2012, and Jimby et al. 2015, and so on, So I don't know what the studies are, but I don't know if Matty, if you could unmute yourself and talk about it, that'd be really interesting because I'm not familiar with these papers you're talking about, but it'd be really good to know about them. Don't see him here. So do you want to comment on that, Eli?
So the first question was, by what mechanism do things diffuse perpendicular to C?
Well, by what mechanism, yeah, does it diffuse perpendicular? Because along the C-axis, he understands that it goes through the channel, but how does it diffuse perpendicular to the C?
Yeah, so I guess.
Oh, so you're saying his microphone doesn't work, so sorry, so you have to do it this way. Sorry about that.
I mean, I'll say right up front that, I mean, this is going to be kind of my best guess based on the data we have. But so something I didn't go over today, just for sake of time, was that we did quite a bit of Zane's work on these samples as well, where we actually looked, measured Zane's profiles, spectra, across these profiles. And we found a few interesting things. So as far as the coordination state of titanium and zircon, it appears to definitely be predominantly 4-coordinated titanium. Now, that either means it's sitting on the silicon site, or these interstitial sites themselves, you predict things to be 4-coordinated if they're sitting on these interstitial sites. According to my colleagues who know Zane's much, much better than I do, we probably could not take this spectra and really determine whether this is sitting on a silicon site or an interstitial site. Either way, though, I mean, my intuition is that it's sitting on these interstitial sites and can diffuse that fast. It's also possible that these things sit on the silicon sites, and perhaps these channelized interstitial sites just really facilitate diffusion hops in that direction. Either way, though, if you're going perpendicular to C, you're not going to have the channelization there to help you out. So I think that's about. I'm not really sure what else to say about that. I don't know if that answers your question at all, but.
Wait to see. So I'll just read out his second question while he gets a chance to type in chat if he has something to say. So the second question is whether the diffusion perpendicular to the C-axis occurs via the replacement of zircon by titanium. Well, we were just talking about that.
Yeah, no, I don't think so. I mean, just comparing, this is, so on the bottom here, we have, the model spectra we should see if we're dealing with 8-coordinated titanium, which is what we would expect if it was in the zirconium site. And we don't see that. We see, the very important features of the model 4-coordinated titanium is what we see here. So I'm quite confident it's either sitting on the silicon site or the interstitial site. My best guess would be that it sits on the interstitial sites. But.
Okay. So are there other questions coming up and things people can think about that? Now, I was going to ask you, Eli, that so that 600 to 800 degree range is where the titanium and zircon temperatures and everything work well. But one sort of messy area is ultra high temperature metamorphic rocks, because those go up to 1100 degrees and they, according to some models, stay hot for very long times. And people have had trouble dating those things and stuff. So do you have a sense from your models what would happen if you held things at 1100 degrees for a few 100 million years?
Oh, yeah. I mean, if you're dealing with, yeah, it would tend to reset your titanium fairly quickly. I mean, at 1000 degrees, 15,000 years, you're already getting pretty significant diffusion. If you hold this for 1 million, you're going to definitely re-equilibrate your titanium concentrations.
So that is one natural setting where we need to worry about resetting of titanium and zircon temperatures.
Yeah, I think there are definitely scenarios where we need to worry about this. There's some scenarios, I mean, if you're getting a 650 degree temperature, unless you've got really small zircons, I don't think you need to worry about anything. And then I think there's a big middle area where, it probably is okay for crystallization temperatures, but we really need to get a little bit more info just to do some due diligence before flat out interpreting things as crystallization temperatures.